Hi, during week 2 I have the privilege of talking about SI unit systems. Really focusing on the prefixes because sometimes as we work through, we don't want to use the base 10, we'd rather use the name that goes with it. As we talk about it, there's some SI base units that we probably should familiar ourselves with. Now, I don't know in your chemistry or physics whether or not you actually used SI units, but if you didn't, this may help you understand where we're going. We'll be using quite a few in college because many of our companies work internationally, and as they work internationally, we have to be prepared to work in SI units outside the US. So if we talk about length as our first, we're talking about inches, feet, yards. Well, in SI, we're talking about meters. And we abbreviate that with a lowercase m. We're talking about mass. You know, you always talk about grams in chemistry, but they're so small. But again, grams is the SI unit, but generally we put a kilo in front of it because they're so small, and a kilo is 1,000, right? And we represent that as a lowercase kg. We also have an amount of a substance. And we use that quite a bit in chemistry, and I'm sure you're familiar with the term of mole. And we abbreviate that as lowercase mol. We're talking about luminous intensity. The reason why I mentioned luminous intensity is because our construction engineers have to go into many structures and figure out how much light do we need. And then, of course, that is because whether it's a lab, whether it's a theater, whether it's a classroom, whether it's an office space, all those light requirements are differently. And the SI is candela, and it's abbreviated CD. Then we have force. We've talked about pounds before. In US units, if we get 1,000 pounds, it's a kip. But in SI, I think you're familiar with it, Newton, and its abbreviation is a capital N. So now as we continue talking about SI units, we want to talk about and remind ourselves of the scientific notation. Now, you spent some time already multiplying them, adding them, but when we start to look at scientific notation, we're talking about a base 10, right? And so we have the factor, we have the name, and we also have a symbol that we should become familiar with, all right? So there's a lot of the numbers here. I'm going to quickly put them up, but again, it's 10 to the 12th, 10 to the 9th, 10 to the 6th, 10 to the 3rd, 10 to the 2nd, 10 to the 1st. We don't always use those 10 to the 2nd, 10 to the 1st as much. 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 6, 10 to the negative 9, and 10 to the negative 12. Now, as we look at each of these, there's a name that goes with them, and this first one is tera, and its symbol is a capital T. That replaces the times 10 to the 12th. A 9 is a giga, its symbol is a capital G. 10 to the 6th, maybe some of these are starting to come back to you, is mega, capital M, as we go through it. 10 to the 3rd, we already talked about that over here, is a kilo. And of course these are all uppercase, this is lowercase. 10 to the 2nd is a hecto, lowercase h. 10 to the 1st is a deca, and this is a da, lowercase. Now as we start to get to these, I think some of these might be familiar with you as you've worked with your some SI units and small numbers. We're talking about deci. We use a little d. We have centi, such as centimeter. There's 100 of those. 10 to the negative 2, 100 centimeters in a meter. 10 to the negative 3rd is milli, lowercase m. 10 to the negative 6 is micro. Here we use a subscript u, or a mu as for it. 10 to the negative 9 is a nano. we use a descriptive in, and then 10 to the negative 12 is a pico, and we use a p. All right? Now that we have these, let's look at an example. And that example is one, as you can see on the picture here, that has a pin at A. We want to know the deflection at B with a load in the middle of 2 kips. Now that's going to rotate clockwise about A. We want to know the deflection, the movement at B, and the rotation at A. Now the first thing we'll do is go through and do equilibrium. We'll also do deformation, equation to give us a second equation, 2 equations, 2 unknowns to solve for the forces at point C and E. And then from there, we'll be able to go back and calculate the deflection at point D and the rotation at point A. So those numbers, just so that we have something to work with, is delta A is equal to 0.0000, and I want to make sure I get this right, 5032003 meters. Now the answer first came out in inches, but I've converted it to meters so that we're working with SI units. And that's delta at point B. Theta at point A is equal to 0.0000, and that is 40262 radians. Okay? So now the first thing we want to do is convert each of these into SI units, and then we want to replace the factor with its name. So starting off, let's just do the deflection at point B. The first thing we did is we got to move the decimal point over to the right. 1, 2, 3, 4, 5, 6. And so as we go through this, we get a number of 3.2003 times 10 to the negative 6 meters. Now we look over here, that is one of our factors, and that is a micro. So we can take that 10 to the negative 6 and replace it with a micro. And therefore our answer then becomes 3.2 micrometers. And that's what we're looking for, as the ability to go back and forth, that a micro equals 10 to the negative 6, and 10 to the negative 6 equals a micron, right? So as we look at a micrometer. Now let's look at the deflection, the rotation at point A. And when we move the decimal point to get it into SI units, we're moving it to the right again 1, 2, 3, 4, 5 times, and we get 2.62 times 10 to the negative 5 radians. Now, as we look at our chart over here for factors, 10 to the 5th is not one that we have here. So we either have the choice of moving the decimal point to the right, 1, or move the decimal point back to the left, 2. Well, generally we want to keep whole numbers to the left of not zeros, and so therefore what we'll do here is let's just go ahead and move it over one more time. And that's going to convert this to 10 to the negative 6. All right? So now we have 26.2 times 10 to the negative 6 radians. And when we look at our chart again, we have micro. If we convert the 10 to the negative 6 to microns, what we have now is theta A is equal to 26.2 microradians. So just as a review of what we did, we looked at some base units, because those units will be in most of our problems. We looked at the factor in our scientific notation base 10. We looked at its associated name. We took numbers that we received, decimal numbers, converted them to SI, and then to scientific notation, and then from there we used our SI unit system to create a replacement for the base 10 with an exponent with a name. In this case, we used micro radians and micro meters. Right? And so with that, good luck on the homework, and see you next week.